what I would like to do here as we start, this is chapter 5, section 2, but it's really in our chapter 3, so a little bit on derivatives. I want to show you that if y is equal to the sine of x, this implies that dy dx is actually equal to the cosine of x. So this is what I want to So to do this, I need two different properties. Now I'm going to prove them both. Property number one is that the limit, as let's say any variable, let's say t goes to 0, of the sine of t over t, that this guy right here approaches the value 1. Okay, so that's the first one I need. The second one I'm going to need to use here is that the limit as t approaches 0 of 1 minus the cosine of t over t, that this is 0. So I need both of these guys. Okay, you'll see why in a little bit. So first I'm going to prove these, and then I'm going to use them in the proof to get this, and I'm also going to use them in the proof to get this. If y is equal to the cosine of x, then the derivative with respect to x is equal to negative sine x. So we're going to get these two guys right here. So let's go ahead and prove this first guy. And what I'm going to do is I'm going to draw you out a picture here. Okay, so let's draw out our unit circle. It's like this. Close enough, right? And let's draw an arbitrary angle. Let's call it theta. So here's the initial, here's the terminal. I'm going to draw on there the line that's tangent out like this. Okay. And so here's what we've got. If we call this, you know what, let me not call it theta, let's just call it t. And that'll keep it the same as what I've got here. So let's call it t. Well, this length running up and down, I'll do it in red. This length right here is the sine of t, whatever the angle t is. Okay. This this white line right here, let's draw it in, let's say, blue. That length right there is literally t, okay, in radians. So if you take the radius, if you take the t value here for the angle and you drop it along here, this right here is t. So the blue line is t. So clearly, as t goes to 0, the sine of t is less than t. This blue guy right here, let me put it in blue. Okay, and that is less than the following. This this purple guy is the tangent. When I say this purple guy, let me do it in actually a different color. Let me grab orange. This length right here, okay, this length right here is the sine, or excuse me, the tangent of this guy. So the tangent of t is this length. And as t goes to 0, the blue line is still larger than the red line, but smaller than the orange line right over here. Okay, so it's trapped, it's stuck between those. So what happens is the limit as t goes to 0 of these guys traps this guy in between these guys. Okay, so now watch what I'm going to do here. I'm going to rewrite this as, let's do it in the right colors here. This is sine of t over cosine t. Still have t in here. And I still have sine t. Then what I'm going to do is I'm going to write everything as reciprocals. I'm going to rotate everything here. So I'm going to go like this. This is 1 over sine t. Now, when I do that, the signs change. You should think about why that is. Okay, so this right here, from here, it follows to here. This is also true. Okay, you pick any t value you want up in this area. This thing right here is going to hold. I promise you that. Like, let me show you an example. Let's let t, real quick, let's let t be equal to, I don't know, pi over 3. Let's go all the way down to pi over 6. Then 1 over, now the sine value at pi over 6 is 1/2, so this guy is 2, which is greater than 1 over t, which is pi over 6. So this is going to be 6 over pi. 6 divided by 3.14 is less than 2. This is going to be less than the tangent value. The reciprocal, if you think about it as cotangent, it's going to be less than the cotangent at pi over 6, which is square root of 3. So if we do all those out, let's pull up. Okay, here's our guy here. Apparently he doesn't want to work. Let's just use this. Just as easy. So 6 divided by pi, yep, 1.9 is less than 2, and the square root of 3 is 1.7, so this holds. Try for a different t value, pick any angle in radians, and I bet you this thing holds. Okay, that's the point. Now watch. Now what I'm going to do is I'm going to multiply everything by sine. Now I can do that because I'm taking the limit as t goes to 0. So this the only time sine of t is 0 is when t actually is 0, but I'm going to take the limit here, so it's not going to be an issue. So multiply everything by sine, so this becomes 1 is greater than sine t over t, which is greater than cosine t. So let me just rewrite this order here. So we've got cosine t is less than sine t over t, which is less than 1. Now the limit as t goes to 0 of this guy right here, the cosine at 0, it's a continuous function, so I can evaluate it there. Cosine at 0 is 1. This guy over here, the limit as t goes to 0 of 1 is just 1 because that's a constant, which means that the limit of this guy at the limits, since it's trapped between those two, we're using what's called the squeeze theorem. So we're saying that, and you can, if you take an analysis course, you'll prove the squeeze theorem, or maybe even in your calculus course, you might prove your squeeze theorem. But basically, it says if the limit of this is equal to the limit of this, and this guy's trapped between these two guys, then this guy has the same limits. So the limit as t goes to 0 of sine t over t must also be equal to 1. So right now what we've got is we've proven this right here. Okay, now let's go ahead and continue. So I'm gonna erase this. Okay. So now we've shown that that first guy in green up there is true. So now let's go ahead and play around with this a little bit. Yeah, I'm gonna get some more room here. Hang on. Okay, so now let's do this guy over here in blue. Okay, so here's what we know. We know that sine squared t plus cosine squared t has to be equal to 1 for whatever t value we pick here. And that's the Pythagorean identity. And this is pretty easy to see because sine measures this red guy right here. Cosine measures this blue guy right here. If you take the blue guy, square it, add it to the red guy squared, you get the hypotenuse squared, and we know that this is on the unit circle, and the hypotenuse here is 1. So that's where we get this from for any t value, okay? So now let's go ahead and take a look at this. We can rearrange some of this stuff. So we can say that sine squared of t is equal to 1 minus the cosine squared t. This over here is a difference of squares. So this is 1 plus cosine t times 1 minus cosine t, like that. And that's equal to the sine squared of t. Now, what I'm looking for is 1 minus cosine t over t. So what I'm going to do is I'm just simply going to divide everything by t, because t is not 0, because we're going to be taking the limit of it. So we'll divide both sides by t. And I want this guy over here by itself. So I'm going to divide both sides by this guy right here. So that's not a problem. So that gives me sine t times sine t over t times 1 plus cosine t. That must be equal to 1 minus cosine t over t. So if these two guys are equal to each other, their limits should be the same. So let's take the limit of this left guy. So the limit as t goes to 0 of this guy, now I'm going to rewrite this as sine t over t times sine t over 1 plus cosine t. Now, I've got the product of two functions here. You can think of this as a function, this as a function, so I can split that using my limits. The only thing I got to make sure is that this guy isn't 0 over 0, but it's not, because the cosine at 0 as t goes to 0, this is 1 plus 1, that's 2, and this is 0. So what I get here is this, sine of t over t times the limit as t goes to 0 of sine t over 1 plus cosine t. And so we just proved that this guy right here is 1. And we know that this guy can just be evaluated directly because this is a continuous function at 0. So when I plug in 0 down here, I get cosine of 0, which is 1. 1 plus 1 is 2. So I get 0 over 2. The whole thing is 0. So that means the limit of this is 0, which means the limit of this must be 0. So we've got this guy right here. Okay, now how are we going to use those? Well, what we're going to do is we're going to write the definition out of the derivative. So let's let y be equal to, let's start with sine x. Okay, so what we want to find is y prime, or dy dx. And if you remember, the definition of the derivative is the limit as delta x goes to 0 of the sine at x plus delta x minus the sine at x all over delta x. Okay. So what I'm going to do right here is I'm going to use my sum and difference formulas for my trig functions. So sum and difference of sine. So here's what I've got. I've got the limits as delta x goes to 0 of the sine of x times the cosine of delta x minus the cosine x times the sine of delta x minus the sine x all over delta x. Now this guy right here is this guy right here, using my difference of sine for the angles. Remember, you can't just distribute sine in here because it's a function. It doesn't work like that. Okay, so this then is equivalent to the limit as delta x goes to 0 of, now what I'm going to do is I'm going to move these guys over. So I'm going to have sine x cosine delta x minus sine x minus cosine x sine delta x over delta x. And then I'm going to, in this first guy, I'm going to take this piece right here and I'm going to factor out a sine x. So that, I'll do it in green here for you, that is sine x times cosine delta x minus 1. And then over here, this guy I'm just going to leave the same, so it's going to be minus cosine x sine delta x. And now the whole thing is over delta x. So we know with fractions we can split them up over the same guy down here. And then the other thing I'm going to do is I've got cosine x minus 1. So I'm going to change that around. Hang on, give me a second. Okay. So this right here, well, I'm going to rewrite the whole thing like this. Limit as delta x goes to 0 of. Now on this first guy, I'm going to factor out a negative 1, and I'm going to get this, negative sine of x times 1 minus cosine of delta x over delta x, minus, this guy in the back is going to be, I'm going to pull out the cosine x, and it's going to be sine delta x over delta x, like that. And now I'm going to distribute my limit in, okay, because my limit laws is I can put it into both these, given that the limits actually exist, which they're going to. So watch. This would be negative sine x, because that doesn't depend on delta x, times the limit as delta x goes to 0 of 1 minus cosine delta x over delta x. And then that's going to be minus, I'm going to do the same thing here, I'm going to pull out the cosine, and it's going to be, because remember, cosine x does not depend, since the limit is as delta x goes to 0, cosine x is independent of that, so that doesn't change at all. The limit as delta x goes to 0 of sine delta x over delta x, like that. Now, what we know from the last example is that this guy right here is equal to 0. And we know that this guy right here is equal to 1. So here I've got 0 times something, which is 0. And here I've got, let's see here, why did that turn out to be negative? Let me just check. Oh, I see. I made a mistake right here. This was plus in here, right? You guys all see that? This guy right here, let's do it in green. This guy was plus, so this should have been plus, which means this should be plus right here coming down. So plus, 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 that looks a lot better. Okay? So this right here is going to be positive, so this is plus cosine x times 1, which is just cosine x. So what we've shown, this is the proof, what we've shown is that if y is equal to sine x, and we want to differentiate this, then dy dx is equal to d dx of sine x, and this is equal to this. So the derivative of sine is cosine. It's pretty slick how that works. It's quite interesting. So let's do one more. So now we need to check the following. Let's say y was equal to cosine x. We want to show that dy dx, which is the derivative with respect to x of cosine x, is equal to negative sine x. So we'll go through that process again. The definition of the derivative is the limits as some variable we'll call delta x goes to 0 of, this time it's going to be cosine because that's our function, so it's going to be cosine x plus delta x minus cosine x over delta x, like that. Now we'll use our sum and difference here. Okay, so this will be the limits as delta x goes to 0. This is cosine x cosine delta x. Now we switch signs, so minus sine x sine delta x minus cosine x all over delta x. Okay, so this right here, what we're going to do is we're going to move it, just the same trick, we're going to move this cosine x over to the front, so this is the limit as delta x goes to 0 of cosine x cosine delta x minus cosine x minus sine x sine delta x. The whole thing is over delta x. Now this piece right here, we're going to go ahead and factor out what we don't, where it wasn't common here, so cosine x. And so that's one, excuse me, that's not one, it's cosine x. Cosine delta x minus 1 over delta x. I'm going to split these guys up, then minus, and this right here is going to be sine x times sine delta x over delta x. Now this, we'll go ahead and we'll factor it to negative 1. So this is the limit as delta x goes to 0 of, actually before I do that, I'm going to factor out the cosine x. So I'll go cosine x, because that's not dependent on delta x. So this times the limits as delta x goes to 0. I'm also going to factor the negative out of this, just pop it out front here. Okay, and that's 1 minus cosine delta x over delta x minus, now it is minus this time, minus, pull out the sign because that's again not dependent on delta x. So this would be minus sine x times the limit as delta x goes to 0 of sine delta x over delta x. And so this guy we know, that guy right there is 0. So what I have is negative cosine x times 0 minus, now this is going to be sine x, and we know that this guy right here is equal to 1. So we're going to go ahead and plug that in, times 1, and so this ends up just being negative sine x. So if we have a function y which is equal to cosine x and we want to differentiate it, then d dx of y is the same as d dx of cosine x, and so dy dx is equal to this guy, negative sine x. And there you've got your derivatives for your cosine and your sine.